The James Webb Space Telescope, JWST, has recently made an intriguing discovery. It has detected artificial light on the distant exoplanet Proxima b. Using its MIRI mid-infrared instrument, which is highly sensitive to infrared radiation, JWST is capable of identifying large artificial light sources on far-off planets. This marks the first solid evidence of potential technological markers, possibly signs of intelligent life, on another world. MIRI's high-resolution capabilities allow it to detect urban lights and advanced structures, not only in our neighboring system, Proxima Centauri, but throughout the known universe. The ability to identify such artificial light is a significant step forward in our quest to explore far-off exoplanets for signs of life. With JWST's advanced instruments, we can now detect vast settlements and potential extraterrestrial cities in the universe. Looking ahead, the launch of the Extremely Large Telescope (ELT) in Chile in 2028 will push these capabilities even further. The ELT, with its 39-meter primary mirror, will provide even deeper and sharper views of the universe than ever before. These advancements are crucial as our desire for knowledge about the universe continues to grow. We are just beginning to explore distant worlds, and instruments like JWST and the ELT will be vital in searching for signs of life, from artificial lights to more subtle biological markers. With these technologies, we are also on the verge of detecting vegetation on distant planets. By studying the spectral fingerprints of planets, these telescopes will allow us to gather evidence of biological processes on distant worlds. Our search for life will evolve with better tools and techniques, and one day we may even make contact with other civilizations. The detection of artificial light on Proxima b represents a milestone. For the first time, scientists have observed light markers from a planet in another star system that suggest the presence of advanced life forms. The JWST's sensitive instruments could even analyze our own planet's activities based on our distinct light signatures. With its ability to detect light from major cities like New York, Rio de Janeiro, or Beijing, the JWST can differentiate artificial light from natural sources, such as the glow from airports, industrial plants, or space stations. For Proxima b, this marks the first time artificial light has been detected, revealing the potential presence of technology and advanced life forms. This breakthrough opens new possibilities in our search for life beyond Earth. We now have the tools to study other worlds with remarkable precision, understanding not just where life exists, but how advanced that life might be. In the future, the development of quantum computers and quantum communication will allow us to send messages across space. If we were to send a message to Proxima b, it would take over 4 years to reach its destination. However, with quantum communication, we might one day be able to contact distant civilizations as if we were communicating in real time. This idea may sound like pure science fiction, but it's becoming more feasible with each scientific advance. Just a few years ago, simulations were predicting that the JWST might one day study the surface of Proxima b. Now, these predictions are becoming a reality. The JWST is capable of performing regular and detailed observations of Proxima b, including examining whether the planet has a life-supporting atmosphere. Proxima b orbits its star, Proxima Centauri, in a way that one side always faces the star while the other remains in shadow, much like how our moon orbits Earth. This could result in extreme temperature differences between the day and night sides of the planet. However, simulations have shown that if Proxima b has an atmosphere, it could help distribute heat more evenly, potentially creating a habitable strip along the planet's equator. The JWST's ability to analyze the composition of an exoplanet's atmosphere is another breakthrough. While we haven't yet detected artificial light on Proxima b, the JWST has already provided detailed atmospheric profiles of other exoplanets, such as K2-18b, where it found signs of water vapor, carbon dioxide, and methane, potential indicators of life. Most excitingly, the detection of ozone could be a powerful biological marker, as it is primarily produced by biological processes on Earth. While we have yet to find artificial light on other planets, the search continues. Not all life forms are necessarily advanced enough to produce such signals. There may be simpler forms of life, like plants or microbes, on planets that we currently cannot detect using technological markers alone. The JWST's ability to analyze the spectra of reflected light and atmospheric composition will help in identifying indirect signs of life, such as plant growth. This technique, known as the vegetation red edge, VRE, allows researchers to detect plant life by examining changes in the light spectrum reflected by a planet's surface. As our ability to analyze distant worlds improves, we will continue to refine our methods and develop new instruments to uncover the mysteries of life beyond Earth. Produced by the intelligent properties of plants in just the beginning of a new era in our exploration of the atmosphere of an exoplanet and is reflected by its surface. Specific patterns in the reflected light could indicate the presence of chlorophyll or other photosynthetic pigments. Detecting such signs remains a challenging task, requiring highly precise measurements and high resolution, which can be affected by atmospheric disturbances and the signal-to-noise ratio. Although the James Webb Space Telescope, JWST, is designed for such measurements, we are just beginning to utilize these capabilities. Scientists are gradually improving their ability to detect and identify signs of life in space. These are exciting times as the JWST has already sparked a revolution in space exploration. However, directly detecting plant growth or biological activity will require future telescopes and missions specifically designed to search for biosignatures. One example is the upcoming LUVOIR, Large UV/Optical/IR Surveyor, telescope, which aims to study the atmospheric properties of exoplanets with far greater accuracy and detect potential biosignatures, such as vegetation-related infrared signatures. LUVOIR will have the capability to isolate and analyze light from exoplanets far more effectively than the JWST, covering a broader range of frequencies to conduct detailed spectroscopic analysis necessary to identify plant or biological activity, potentially even on planets like Proxima b. You may be wondering how the Extremely Large Telescope, ELT, will examine Proxima b, given that it is still under construction in the Atacama Desert in Chile. The answer is simple. Researchers have already developed simulations showing how the ELT will observe the sky long before it launches. With its remarkable 39-meter primary mirror, the ELT will become the largest optical and near-infrared telescope on Earth, expected to begin operations in 2028. The ELT is specifically designed to analyze the atmosphere and surface properties of exoplanets with high resolution and light sensitivity. It will be able to detect faint signals from distant planets, similar to the JWST, by utilizing adaptive optics to correct atmospheric distortions, providing sharper images and more precise data. For Proxima b, this means the ELT will be able to perform detailed spectroscopic studies of its atmosphere, identifying the composition of gases like water, carbon dioxide, and methane, as well as searching for biomarkers. The ELT's ability to use direct imaging techniques will also allow it to detect artificial light or prominent surface features that could indicate life or even advanced civilizations. The key difference between the JWST and the ELT is twofold. While the JWST is focused on infrared astronomy and operates from space, the ELT is a ground-based telescope with a much larger aperture, offering higher resolution in optical and near-infrared wavelengths. The JWST excels at observing deep infrared sources and studying the early universe, while the ELT will push exoplanet research further, providing more detailed insights. The LUVOIR telescope, which will be placed in space, will also focus on detecting exoplanets and searching for biosignatures like vegetation-related infrared signals. Another significant project currently under development is the Habitable Exoplanet Imaging Mission, HAB-X, which will capture the first images of Earth-like exoplanets and study their atmospheres. The quest for extraterrestrial life has captivated humanity for centuries, and technological advancements have brought this search closer to reality than ever before. Before the launch of the JWST, the focus was on building powerful telescopes that could peer deep into space and reveal details about the atmospheres and surfaces of exoplanets. The JWST, equipped with cutting-edge infrared instruments, is a major leap in our ability to explore distant worlds and potentially detect signs of life. One of its main goals is to conduct detailed spectroscopic studies of exoplanets, searching for biosignatures like water, carbon dioxide, methane, and possibly even ozone. These biomarkers could provide strong evidence of biological activity, hinting at the presence of life elsewhere in the universe. By studying distant exoplanets, Scientists hope to better understand planetary formation, evolution, and the potential habitability of other worlds. Beyond its scientific goals, the JWST also has the potential to detect technosignatures, artificial signals that might indicate the presence of advanced civilizations. For instance, the discovery of artificial light on Proxima b would highlight the JWST's ability to detect large-scale industrial or urban activity on distant planets. This ability opens new avenues for understanding how civilizations develop and evolve across the universe. Looking ahead, future telescopes like the ELT and LUVOIR are poised to revolutionize our understanding of exoplanets and the potential for extraterrestrial life. The ELT, with its massive 39-meter primary mirror, will provide exceptional resolution and sensitivity in optical and near-infrared wavelengths. Set to begin operations in 2028, it will complement the JWST by offering sharper images and more detailed spectroscopic studies of exoplanet atmospheres. Meanwhile, LUVOIR, designed for space-based observations, will directly image Earth-like exoplanets and analyze their atmospheres for signs of life. These future missions represent the next frontier in astrobiology, offering hope that we may one day discover definitive proof of life beyond Earth. In addition to technological advancements, the search for extraterrestrial life also raises philosophical and ethical questions. How would humanity respond to the discovery of intelligent alien civilizations? What implications would this have for our understanding of our place in the universe? These questions underscore the profound impact such discoveries could have on society and culture. Furthermore, the development of quantum technologies holds promise for revolutionizing communication with potential extraterrestrial civilizations. Quantum communication, with its ability to transmit information instantaneously over vast distances, could enable real-time communication with beings from distant worlds. While still in its early stages, quantum communication offers a potential pathway to interstellar communication and collaboration. In the end, the study of exoplanets and the search for extraterrestrial life are among the most ambitious scientific endeavors of our time. With each technological leap, from the JWST to the ELT and beyond, we move closer to answering humanity's age-old question: are we alone in the universe? As we continue to push the boundaries of space exploration, we may soon uncover groundbreaking insights into the diversity and potential for life beyond Earth. The journey to find our cosmic neighbors is just beginning, and the discoveries that await promise to reshape our understanding of the universe and our place within it.